Hello. Today I want to show you some of the research about AI upscaling for CGI that we've been working on at Hochschule der Medien as part of the KI-Lab Animation and VFX. The KI-Lab Animation and VFX is a collaborative project between Hochschule der Medien as well as the Research and Development Department at Animationsinstitut of the Filmakademie Baden-Württemberg. It's been funded by the Wirtschaftsministerium Baden-Württemberg. The goals of our KI-Lab project were to explore how the recent advancements in AI technology could be applied to practical use cases in existing CG pipelines in order to improve workflows and productivity. In addition, we provided consulting services for local VFX and animation studios. One topic we took a deeper look into was image upscaling using deep neural networks. The state-of-the-art research has been achieving increasingly impressive results over the last few years. At the same time, more and more commercial tools for upscaling photos, videos, and game renderings are being released using some kind of AI technology. Currently, none of them provide the necessary features and fulfill the requirements to confidently apply them in a real-world production scenario. We took a look at the most promising research and tried to use and adapt it to real-world production data supplied by the local animation studio Mark 13. But first, let's have a quick look on the results achieved on previous research. For the image super resolution task, the best results in recent years have been achieved by sRGAN and ESRGAN among others. With an upscaling factor of 4 and based on low resolution input image, they can reconstruct even fine details like hair and fur with almost no perceptible difference to the original image. But these approaches generally won't work well on videos as each individual frame will be scaled without regard to its surrounding frames and therefore generate artifacts such as flickering. There are various approaches to fix this problem and achieve similar quality results for the video super resolution task. One of the most prominent ones is Tekogan, based on the paper Learning Temporal Coherence via Self-Supervision for GAN-Based Video Generation by Chu et al. From the Technical University of Munich. They apply a sophisticated recurrent GAN architecture with a complex loss term to achieve a high scaling factor of 4 with high quality results and temporal coherence. You can see how Tekogan is able to reconstruct fine details in the actor's face, like eyes, as well as reconstruct the railing of these stairs in the background based on just a few mushy pixels. If those same results could be consistently reproduced on full CGI renderings for VFX or animation work, productivity could be increased immensely by saving a significant amount of render time. To produce a full HD output image containing roughly 2 million pixels, we could render a low-resolution 270p image containing around 130k pixels and upscale with Tekogan to generate the same resolution output. This could mean saving over 90% of the render time compared to rendering the full resolution in the first place. To evaluate the performance on a practical use case, the local animation studio Mark 13 supplied us with actual production renderings to train and test with. It consisted of just a few minutes of full CG animation footage in a specific miniature and stop motion style. First, we tried upscaling a downscaled version of the animation footage with the original Tekogan model supplied by its authors. At first sight, the results look alright, but on closer look there are quite a few artifacts in the output, especially when there's a still camera, which is a big part of our existing data. We suspect this happens because of missing or underrepresented still camera footage in the original Tekogan training data. We retrained a model with our own training data and could reduce artifacts and improve overall quality. But technically, there's still a difference between this application and a production use case. Looking at the original Tekogan architecture, the training works solely based on a high-resolution input video, which is downscaled via Gaussian filtering during the training process. The model then learns to recreate the original high-resolution input from the downscaled video. In a production use case, we wouldn't have the high-resolution input to downscale from, but instead just use a low-resolution rendering, which we want to bring to a high resolution. Although the scaled and the rendered low-resolution video are very similar, they are not identical, as you can see here when you calculate the difference between the two. We assume that adapting the model to use actual low and high resolution video pairs for training will achieve higher quality results for our use case. To test this theory, we received additional newly rendered training data as low and high resolution video pairs. Then we adapted the network architecture to train this with new data. The full training process of a model took around 2 weeks on an NVIDIA 280 Ti graphics card. We also trained another model on the new training data with an architecture based on the original downscale training approach to compare our results. The model based on the original downsample training data produces detailed results, but also tends to introduce some kind of grain and high frequency details which are not in the original high resolution data. This is especially noticeable on the character's skin and in the darker parts of the scene. The model trained with the paired data also produces detailed results, although the image is a bit softer. At the same time, there's less unwanted grain and artificial high-frequency patterns compared to the previous model. Again, this is especially apparent when looking at the character's skin. The suboptimal performance of the cave area can be attributed to these kind of areas being underrepresented or not existing in the training data. Here's a look at the original high-resolution rendering that was used for training. This is a look at the output of the two trained models and the high-resolution rendering side by side. Although these results look promising, there's still a lot to be improved to consider this approach for widespread production use. The main limiting factor was the small amount of training data we had, as well as its limited diversity. For any animation or VFX studio, it should be possible to generate a multitude of further training data and therefore potentially generate higher quality results. Another improvement could be made by generating higher quality renderings at the expense of render time. Furthermore, more data augmentation during training, like random color shifts and transformations, could lead to better generalization even with a limited amount of training data. In addition to enhancing the training data, there are various changes to the neural network that could lead to improved performance. For example, reducing the scaling factor from the quite extreme amount of 4 to a more reasonable factor of 2 could help with achieving usable results, but also causing less render time savings. Another consideration is the bit depth and color space of the input and output data. The original architecture is limited to 8-bit sRGB input and output data. We changed this to 16-bit, but working with fully linear 32-bit images would be desirable. Lastly, adding additionally available input data, such as motion vectors or depth maps, could help the network in analyzing the image and creating better results. We hope you found our research interesting. Thanks for watching, and thanks to our project partners at Filmakademie Baden-Württemberg and the funding from Wirtschaftsministerium Baden-Württemberg.